What's up, YouTube? I see we got a couple people waiting for this stream. Hell yeah. Nice to see you. Welcome to my practice stream. My name is John. I am a former math major turned software engineer, and then AI took my job. So now I am practicing mathematics on the internet. It's my love, my old passion. I'm trying to rebuild the habit and the hobby of studying mathematics. So we have been working through linear algebra for the last couple of weeks or so. I'm working through this book by Frale. Today we're going to begin chapter 4, and I freaking love this book, man. What's up, Bloodfire? How are you? How do you find this book? This book is the book that my class taught out of like 15 years ago. So this was the book that my class taught from. It's great. This book is really, really good, man. Like, it's nice. It's introductory linear algebra. It's not abstract, theoretical for a math major. Like, this is linear algebra for engineers, but it's written for potential math majors. Like, it is truly, like, mathematically clean and organized. It's a super nice book so far. So I'm a big fan of this book. Dude, 2017X, what's up, man? 2017 has been following me, hopping across 3 different channels now. I've been streaming a lot today because I got a lot of free time. So let's start chapter 4 on determinants. You know what's crazy? A couple days ago, I streamed and Luna turned off the stream. My cat turned off the stream. So I was streaming to nobody. I was taking all of these notes about the cross product, about, you know, so let's just recap a little bit the notes on chapter 4. So we are learning about the concept of the determinant. And what is a determinant? Perfect. I'm glad that you asked. And hey, what's up, Alex L? So what is a determinant? Great question. So if you have 2 vectors, A and B, the determinant of a matrix that has those 2 vectors in it would tell you the area of the parallelogram that they create. Okay, so if I have those 2 vectors, then if you think of the parallelogram that they would create, like over here, a second copy of B being attached to the end of A, they create a parallelogram, right? Let's go, fire, lol. Yeah, dude, this is the nerdiest thing in the world, y'all. Like, this is a math practice stream. I'm not a professional mathematician, but yo, like, if you all want to study linear algebra with me, and like, I can try to teach you all some of this stuff, hell yeah, this is so nerdy. So, this is the determinant of 2 vectors. And if you do the geometry argument, you can see that we can calculate what the area of that parallelogram would be. It would be the length of vector A times the height of this parallelogram. And you can see that. Why would it be the length of A times the height? Well, so here, if you see this one as a parallelogram, right? A parallelogram has these 2 right triangles, and you just move one of those right triangles over to the other side, right? So here, like if we just moved that one right triangle that was over here and moved it over, now this is a rectangle, right? And then this bottom length is the length of the vector A, and then the height we calculate based on this right triangle with B. So there we have a formula for the area. We run through some calculations, and then whatever area we end up finding is this. So this we call the determinant of this 2x2 matrix. A1, A2, B1, B2. And dude, I will never memorize this in my entire life. But the way that you do a determinant of a 2x2 matrix is the forward diagonal A1 B, oh wait, sorry. Yeah, A1 times B2 minus A2 times B1. Okay? This is the determinant of a 2x2 matrix. So this is a second order determinant, a determinant of a 2x2 matrix. Then this section defines the cross product of two vectors. So what a cross product does is if you have two vectors, it'll find a third vector that is perpendicular to both of them at the same time. So over here, there's another figure in the book that has some vectors, B and C, and then the cross product of B and C creates this perpendicular vector to both of them. Wait, how do you make parallelogram from two vectors? Yeah, no worries, man. Dude, I've been streaming with nobody watching. Like, it's so much better if I can try to explain to people who are watching. Yeah, if you want to see it, I can show you. So, I'm going to draw two random vectors, right? Like here and here. So, vectors we think of as arrows that start from the origin and then they point to a certain direction. So they have an angle, and they have an angle from the origin, and they have a length, right? So if this vector is A and this vector is B, right? Then if you add another copy of B to A, then this creates a third vector. This would be B plus A, or A, well, I like the alphabet, so let's use A plus B, alphabetization. So if you add a vector to another, like notice I just kind of added another copy of B from the end of A. So you add vectors like tip to tail. Like the tip of A touches the tail of B, and then this would give you the third vector, A plus B. Same thing, if I add A to B, then that would give you this other side, right? So then this line is going to be parallel to this line, and this line is going to be parallel to this line. Therefore, that is the definition of a freaking vector, or a parallelogram. That's what I'm trying to say. So, yeah. Does that make sense, dude? These two are parallel, and then the other two are parallel. So that creates a parallelogram spanned by two vectors. Yeah, if you ever need help with algebra, please, dude, shoot me a question. I'd love to help you all with your homework. I'll help you cheat. Like, dude, if you want to cheat on your homework, you can just ask ChatGPT. Like, at least you could cheat with somebody trying to actually teach you, and you might be able to learn a little bit better. All right, so, and then if we wanted to know the area of this, then we go through all those calculations, but what the determinant says is it A1, A2, B1, B2. The determinant is this diagonal, A1, B2, minus this diagonal, A2, B1. And the area, this number can be negative, so it's the absolute value of this thing, right? So that number can be negative. So the absolute value of that number is the area of that parallelogram. So in 3 dimensions, we can create the cross product, and then we end up finding the volume of a box is very similar. If you want to calculate the volume of a box like this thing, you do something very similar. but it ends up being the determinant of a 3x3 matrix. By the way, why did you stop using Shilov's book? Dude, because it's too hard, bro. Like, it's too hard. I'm so rusty. I liked Shilov, but I visited my parents over the holidays, and dude, like, I just love this book. This is the book that I learned from, and this book is just going to be more accessible to you all, to like all of us. Like, I'm rusty. This is a good introduction to linear algebra. Shilov would be like a second course in linear. And like, dude, I'm rusty. I want to just do a first course. Shilov is like written for mathematicians, whereas this is written for, okay, let me phrase it this way. Dude, Streng is written for engineers, right? Streng is like the really popular, famous one. Streng is written for engineers. This is written for engineers and trying to convert them into math. Like, I changed my major from engineering to mathematics because of this class, because of this book, because of my teacher. Like, I was a chemical engineer, and then I took this class, and I was like, fuck, I guess I'm a math major now. Like, this is beautiful. So, like, dude, oh, you found me because of Shilov? Yeah, man, let me grab it real quick. Yeah, this book is badass. Like, dude, it's still right here. I'm ready to study it someday again. Like, dude, page 1, Shilov is just like, fuck your feelings, let's learn determinants on page 1. And he's just like, do not care. Chapter 1, page 1. Like, Shilov loves determinants. This is literally page 1, bro. Like, he's just like, and it's crazy. He's just like, let me just throw the hardest determinant problems you've ever seen in your life at you. And I was just like, this is not the book I was looking for, man. Like, it was fun. I solved all of the problems in chapter 1. I solved all of them, but dude, they're hard. Like, I'm a math major. I love this stuff, but like, dude, this isn't what I was looking for baby math, you know? This is one of those books where, like, in the whole chapter, there are 14 problems at the end of the whole chapter. Like, that's not the kind... This is, like, legit math major math book. Like, a math major math book can fit in your hand. It's small. It's a small book like this. And, dude, like, it'll have 14 problems for an entire chapter. Like, dude... Chapter 4 on determinants in this book has... Alright, I'm in section... first off, determinants are in chapter 4, not chapter 1. And the very first section, which is just motivation, has 63 problems and 4 programming problems. Like, this is the kind of book that I'm looking for. I want something that has 63 problems in a problem set, and then in section 2, the determinant of a square matrix, there are 39 problems. Like, and then section 4, there are, you know, you get the point. You get the point. There are 36 problems in section 4. Like, this is the level of math that I'm looking for. You know what I mean? After you finish streaming, I'm gonna have been to 90 channels, lol. Oh yeah, after this one, we're going to another channel, and then we're just going to keep rinsing and repeating until we all die. Yeah, I'm just gonna keep making a new channel constantly here. 2017 just met me today in like my guitar channel earlier today, and he joined me on my gaming channel. We played some music games. I took a break, and now we're streaming mathematics because I'm a gosh dang nerd. Okay, so what I did last time, even though the cat turned off the stream, I wrote down this theorem about cross products, and I don't remember any of this stuff, so this is good for me. So let's get started. Let's start solving some problems. Dude, Bloodfire, have you been watching me since the old Shilov videos? Because, like, I started this channel, like, a year ago, and I was doing some problems, and I was like doing some practice streams and whatnot, and then I threw it away, and now I'm coming back. Dude, I just want to build up the habit and hobby of math, because I just love math, y'all. Alright, so exercise 1. This is easy. Alright, so number 1, I'm going to say Frale. This one's nice. 4, 1. This is the kind of problem that I'm looking for. It just says, find this determinant. -1, 3, 5, 0. So again, we multiply by diagonals. -1 times 0 minus 3 times 5. And that would be -15. Cool. Done. Done. So here's a little gimmick. I'm crossing out in pen on my book every time I solve a problem. We're going to solve every single problem in this book. All right, 4.2, the determinant of a square matrix. So, yeah, we're getting a lot of calculation problems in this book. Frale 4.2.1. So now we're getting into some bigger matrices. Find this determinant. 5, 2, 1, 1, -1, 4, 3, 0, 2. 3, 0, 2. Okay, so now something like this, there's a couple ways. We can do expansion by minors. I'm going to solve this 2 ways. First, expansion by minors. Not like the Epstein minors, but just like, minor cofactors of the matrix. So I'm going to expand along this first row. So this determinant of that matrix is going to be 5, which is that cofactor. 5 times the determinant of the remaining matrix if I cut out that row and column. So 5 times -1, 4, 0, 2. And this is an alternating thing. So now we can erase. And then now we march on to this one. We still cut out that row and that column. So we subtract 2, which is that cofactor that I circled, times the determinant of the remaining numbers, 1, 4, 3, 2. Okay. Now let's erase. Oh wait, I keep erasing the wrong one. So we slice out that thing. We're going to circle this cofactor. So we're going to add 1 times the determinant of the remaining matrix. 1, -1, 3, 0. Like this. How's the music audio levels, by the way, y'all? Because this is the first time I'm ever trying, I've been trying like background, like lo-fi hip-hop. So, oh, dude, you've been doing fundamental theorem of algebra? That stuff is beautiful, dude. Fundamental theorem of algebra is beautiful stuff. That is super cool. That's great that you're learning that. That looked like a cat straight walked on your keyboard. Lol, that's funny. I've been wanting to hop on in streams as well, but busy life, yeah. So don't worry about it, 2017. I'm trying my best. I'll teach you a couple things, 2017. Yeah, I can, because we're in chapter 4, but I could tell you some things from chapter 1. Like, we're chilling. If I finish chapter 4, we'll start over, and I'll do some problems from chapter 1. How about that? Okay, so now, here, why don't we do this? In red, we've got 5 times this diagonal, negative 1 times 2 minus 4 times 0. Okay? In blue, we have negative 2 times 1 times 2 minus 4 times 3. And then in purple, we have plus 1 times 0 minus negative 1 times 3 plus 1 times 3, right? So does that make sense? Do you see how I'm like doing these things? Does Frale go over why do it like this, like proof of this method or something? Yes. Frale does a good job of actually including proofs, usually. So, cool, man. Like, hey, you're learning, even though you're a 9th grader. So you see how it's like the forward diagonal minus the reverse diagonal. Like the negative slope diagonal minus the positive slope diagonal for each of these. So now we just calculate these. So this is going to be negative 10. This other one is what? Negative 12 plus 2 is negative 10 times negative 2 plus 20, right? And then this last one is plus 3. So this looks like it's 13. Let's check in the back of the book. Am I a smarty pants? Did I solve it right? Am I a smarty pants? This book has a lot of solutions. I think all the odd numbered problems have the solutions in the back. What the? Oh wait, no, that's 4. Yeah, we got it. 13. Hell yeah. Hell yeah. So I'm going to cross out this problem from the book. We did it. Nice. Now, section 4.3, computation of determinants and Cramer's rule. Ooh, okay. I don't know what the difference is because I haven't read the section, but I did say that there's 2 ways to do this one. So why don't we see part B, the shortcut for 3x3. This only works for 3x3 matrices. I plan on streaming for about an hour. Probably, I want to try to get through chapter 4. There's 4 sections, so probably 4 problems. This only works for 3x3 matrices, and I remember that when I was doing my Shilov problems, and I got confused about something. But we have, I'm going to copy this. Y'all, I've been sick, but I'm slowly getting better. Okay, so let's copy that thing. Let's erase. So if I find the determinant of this thing, yeah, I was a chemical engineer, yeah. And then in semester 1, I realized I don't like chemistry, and holy crap, I really like math. And then I turned into, yeah, it was viral. Man, dude, this has been rough. It's been 2.5 weeks that I've been sick. It's been hard, dude. Okay, so what we do is we're going to add an extra copy of these 2 columns. This is kind of like a shortcut that just works. 513 2 -1 0. And yeah, I don't know. I would do something like this. I don't know the best way to present this. But now this only works for 3x3s, but it's a super cool trick that works. This is going to equal 5 times -1 times 2 plus 243 plus 110 minus, let's do this in yellow, minus 1 negative 1 times negative 1 times 3 plus 540 plus 212. And when I'm saying 212, I mean 2 times 1 times 2. I'm just being lazy, you know? So then this is negative 10 plus 24 is 12, I think. Is that right? Did I do that right? 24, yeah, 24 minus 10 is 14. What am I talking about? Yeah, 14. Here we go. Minus, what do we have here? Negative 3 plus 4. So we have minus 1, right? So now we have, the answer is 13. Yo, look at that, 13 again. Is this, oh wait, I was doing the same matrix, so that makes sense too. You said you were a software engineer too when stream started. Yes, yeah, exactly. So I studied math. I went through a whole math degree. I was originally planning on becoming a math professor. I loved it. I did pretty well. I did a lot of master's level math, but then, dude, the iPhone had come out and I was like, yo, this iPhone thing is going to change the world. I want to learn how to program for that thing. And then I decided I wanted to learn coding and get into iOS app development. That was a good career decision, man. Like, yes, the iPhone turned out to, change the world quite a bit. So I worked at Apple, I worked at Lyft, and then I worked at Google. And then Google laid off my entire team because of AI. So AI took my job, and now I'm a classical guitarist and a math YouTuber. So it's actually kind of a dream come true right now, because I get to try to pursue my creative love and my hobbies like math and guitar. But yeah, software kind of sucks right now, dude. Software is just kind of in a weird place. But yeah, I'm trying to get back into math. I just want to teach math. I want to teach like little kids math. Like AI is not going to take that. Like, you know, a motivational coach like who can motivate a 9th grader or like a little kid to enjoy math. Like, dude, AI is not going to take that. And he does gaming streams. Yeah, dude, I do. That's a brand new thing, but yes, I do have a gaming stream. youtube.com/@classical. Oh wait, no, JC Practices Gaming. And that's music games. I mean, the important one, y'all, is my guitar channel. I don't know about important. I don't know if I want to say that, but that's my main one. youtube.com/@JCPractices is my guitar. You want to see some more games? No, dude, math can be your video game. That's what I'm trying to teach you all. Math can be your video game. It's so fun. Like, dude, there are geeks out there who just love doing Sudoku on the plane, right? I do math on the plane. Like, I do math for fun. Like, it's study time. Yeah, after math is done. We'll probably go back to guitar after math is done. Okay, so, I don't know, maybe we could do more gaming. Excuse me. Frale, 4.3.1. So now section 3. I don't know what the difference is on this one, but it says find the determinant of this matrix. You can either write determinant with bars like I was earlier, or determinant with parentheses like this. Either way, whatever you want. -3 to -1. Okay. I like the bar approach. 2, 3, -1, 5, -7, 1, -3, 2, -1. So I think now is a good chance to show some calculation stuff. Maybe you should make stuff using linear algebra, ChatGPT. Dude, like AI is literally all linear algebra. AI is all linear algebra. It's giant matrices being multiplied together. Dude, 2017, did you say that you're going to go into teaching? Dude, that's awesome. That's cool. I didn't know that. All right, so a property of the determinant is that you can add and subtract rows to one another, and it will keep the same value of the determinant, which is neat. The teaching I'm going to be doing is going to be a gaming teaching. Oh, that's weird. Teaching gaming? Is that a thing? Do people do that? Okay, so how does this work? How exactly does this work? So what I can do is 2, 3, -1. I'm going to keep that first row the same. On the second row, I'm going to subtract 2 copies of the first row. So so I'm going to write it over here. R2 prime, I'm replacing the second row right now. I'm computing this determinant right now. So I'm going to replace the second row by row 2 minus 2 times row 1. Okay, so I'm subtracting 2 copies of the first row from the second. So then 5 minus 4 is 1. -7 minus 6 is -13. And then 1 plus 2 is 3. Follow me? You got that, everyone? All right. Now, let's do row 3 prime is, I'm going to add the first row to the third row. Row 3 plus row 1. So I'm going to add the first row to the third row. So if I add the first to the third, then we have -1, 5, and -2. And the amazing thing is that, hey, Heidi's in the chat too. What's up? Heidi's a longtime regular of the math or of the guitar channel. Good to see you, Heidi. We're learning about the determinant, which is a mathematical object that will tell you the area of a parallelogram. It will tell you the volume of a box. But kind of more interestingly, it tells you if a system of equations is invertible or not, and some other cool things. Yeah, the determinant is a really neat thing. So now we could... another property. So, excuse me. I'll write what I'm doing here. So, 1, properties of the determinant. Adding a multiple of another row does not change the value of the determinant of the matrix. Okay, so this is one really cool property, and that's what I just did here. So I replaced the second row, I subtracted 2 times the first row from the second, and I added the first row to the third. Another neat property of the determinant is swapping or interchanging 2 rows Also, this stuff works with columns. Changes the sign of the determinant, okay? So what I'm going to do right now is I'm adding, I'm going to swap the first and second rows. So since I'm swapping two rows, it changes the sign. 1, -13, 3, and 2. Why do I want to do that? I like having a 1 in the top. I don't know, I just do. And then, yeah, so let's just complete this thought. 2, 3, -1. So I changed row 1, the new row 1, I replaced with row 2, and the new row 2 was row 1. And while I'm at it, I'm going to go ahead and use this first property again. And I'm going to add R3 prime is R3 plus R2. R2 from the previous matrix. So I'm adding the second and third rows together to get a 0 in this place. 1 plus -1. And then -13 plus 5 is -8. And then 3 plus -2 is 1. I changed colors because why not, I guess. Now, now this is good enough in my mind. I'm going to expand by this column. So I mentioned that we can do expansion by cofactors. We can either go across one row or we can go across columns. Either way works. Or if I wanted to make this a little bit easier, let's see an example where this works either way. I want to go two different directions. Let's go two different solutions here. Okay, so solution 1, let's do another addition. So doing that property of adding rows to other rows, we could subtract 2 times so if I subtract 2 times the first row from the second, then I have 2 minus 2 is 0. 3 plus 26 is 29. And then we have 6. Wait, -6. Yeah, -6 plus -1. -6 plus -1 is -7. We're getting some weird numbers, but hey, maybe it works. I don't know. 0, -8, 1. Okay, so if we did everything right, then now let's expand by minors, and we'll expand by this and this. So we'll expand by the first column. So this is going to be 1 times the determinant 29, -7, -8, 1. All of this is actually with a giant negative sign in front. Don't forget that negative sign. Minus 0 times this determinant plus 0 times another determinant. So, whatever, those are zeros. And this is going to be negative determinant of 29, negative 7, negative 8, 1. And this is negative 29 minus 56. What is that? Negative 27? So this should be positive 27. All right, let's check our work by doing it with the other approach that I was going to suggest. If we do the same matrix here, copy this thing, bring it down here. I was going to suggest that we could expand by minors here, and if I expand by that first column, then we have negative 1 times the determinant of 3, negative 1, negative 8, 1, minus 2 times the determinant of negative 13, 3, negative 8, 1, and then plus 0 times some other stuff. 0 times a determinant. Well, 0 times anything is just 0. Math is now low-key just better when explained by a person that isn't as demanding as a teacher. Bro, that's the goal, man. Like, math can be fun, math can be chill, math does not need to be such a high stressor, stressful, traumatic kind of experience. Like, dude, like, math is fun. Like, in 20 years, when you're an adult and you have to have a deep hobby, or like when you want to pick up a hobby, dude, math is not a bad hobby. It can be fun, especially if there's no deadlines. If you're just doing it for fun, like, math is so fun, man. Like, it's so much better for your brain than other types of hobbies. Like, yeah, it doesn't have to be a horrible traumatic thing, but that's how people know math, right? So, low-key, thank you, man. 3 minus 8, negative 13, minus negative 24. So, this is 5. I'm doing too much all at once. 3 minus 8 is negative 5. Distribute the negative. Plus 2 times 11. Right? So 22 plus 5 is 27. Yo, that sounds familiar. Did we get 27 earlier? We did get 27 earlier. Look at that. Mathemagical right there. 27, 27. So either way works. So that might be a little more confidence that this property of like adding rows to other rows doesn't change the determinant, which is pretty low-key cool, I think. So, if I felt like it, we could expand by minors all the way from the very first one, but like, dude, we don't have time for that. That's kind of boring. You're seeing Iron Lung with a Friend. It's the Markiplier movie. Okay, dude, that's cool. I don't know anything about that. What's the movie about, dude? Alright, so exercise for the reader. If y'all want to try this determinant expanding by minors straight up without adding and subtracting rows, like, be my guest. It's worth doing once in your life, I feel. But yo, we did it. Let's keep going. Frale 4.4.1. I don't know what it's about. You're keeping it a surprise. Yeah, you're just interested because it's Markiplier. Who the hell is Markiplier? What is his deal? Why is he in movies? Who is Markiplier? Dude, teach me. I'm old, man. Like, you don't realize. I'm, like, in my late 30s, dude. I'm in my late 30s. I'm old, bro. I don't know who Markiplier is. I'm too old to know that. I'm the kind of guy who does math and classical music as hobbies. Like, I'm turning into an old man, dude. All right, Frale 4.4.1. This is about linear transformations and determinants. The book says that this section is optional, but now I'm learning all the cool optional stuff. So, he says, find the area of the parallelogram in three-dimensional space determined by the vectors 0, 1, 4 and -1, 3, -2. Ha! Dude, that's interesting. I don't know this one. Yeah, like, who is Markiplier? What's his deal? Is he a YouTuber? Man, so I'm trying to stretch my brain by not reading the section and trying to solve these problems without reading the section. What's confusing to me now is that this parallelogram, because we calculated the area of parallelograms before in 2D space, right? We had examples from before of 2D space. If you have two vectors, A and B, they form a parallelogram with this other vector, A plus B. So, so how can I see this as a parallelogram if it's in three-dimensional space? I'm bad about thinking in 3D. I'm just not the greatest at it. How's this gonna work? So if we have 3D space, I, J, K. So then we have, let's say that this one is V and this one is W. V is 0 in the I component, 1 in the J component, and 4, 2, 3, 4. So it's a vector that points up here. It's kind of coming toward the camera. And then the second vector is -1 in the I component, 3 in the J component. 1, 2, so 1, 2, 3. Something like here, I guess. And -2 shoot. Would that be here? If we have a parallel line there. So I think that it would be like down here. Dude, I'm so bad at drawing 3D. When I'm drawing into like a negative axis in 3D space, I like to use dotted lines for that. So this one is pointing into the page. Like beneath the IJ plane. And I guess that these two form a... Oh, shoot. Okay. No, it's a parallel line to axis. It's a parallel line to axis. Is it? Wait. -1, 3, -2? -2, like the -2 component is -2 in the K direction, right? -1 in the I component. Oh wait, -1, +3, J. So I did that correct. I don't know what you're talking about. All right, so what I see right now is if I take the 2D space, I mean projection on floor. Projection on floor. Like if this plane is the floor, then it's like projecting into the floor. Like it's like going into the floor, right? I'm so bad at drawing 3D space, y'all. But what I see is it's kind of like if we have the I and J R2 and we do a linear transformation into R3 such that we have that these two lie on a plane, like if we have a linear transformation that maps from R2 to R3, then we could consider we would consider the parallelogram, based on, because these two vectors in 3D space that are linearly independent span a plane. So we need, math is low-key good background noise for gaming. Well, fuck yeah, dude. That's the goal, man. Like, if I can make like a ASMR math stream, that'd be so sick. Whatever it is, I don't know how to see it. I think I'm stumped on this one. I'm gonna have to read the section, which makes sense because this is optional. I don't know if my class taught this. But what I see is I need to find... What I need is like some way to find the plane spanned by the span of V and W. And then we need to calculate the 2x2 determinant in said plane, I think. Because a 2x2 determinant is a 2x2 determinant tells you the area of a parallelogram. So if we can find the area of the parallelogram in the plane that those two vectors span, then that would be the answer to this problem. And I think that what I need to find is some linear transformation. Maybe we need a linear transformation from R3 to R2. Yeah, if we do like the projection of not quite a projection, but if we can map from R3 to R2 in a way that preserves these vectors, how would this work? I think I'm onto something here. I'm trying to like figure it out and invent it for myself without checking the section. I think I'm pretty dang close with this idea, because if I find a linear transformation that maps I don't know. Then we would map these two vectors to R2 and be able to T of V would be some new vector v1 prime v2 prime or something. It would be a 2 length vector, and T of W, the transformation of W would then be W1 prime, W2 prime, and then the area of the parallelogram would be the determinant of V1, V2, W1, W2. Right? Like this, I'm so close. I am so close. I'm like, could we just project to the R2 plane? I think we would lose info if we do that. Like just like remove the third component or something. Yo, I think I got it. We can find the third vector that would be perpendicular to V and W. That's the cross product of V and W. How much math are we doing today? I don't know, dude. Bro, I don't know. An hour? This is the last problem, I think, actually. And here is the shortcut for doing this thing. IJK 014 -1 3 -2 -1 3 -2, and then this is this, so -2i plus that -1 is a copied. So minus 4j, and then that last diagonal is k times 0 times 3 plus 0 k3, and then we subtract these red lines. Negative k plus 12i plus 0j. Y'all, we're getting close, I think. Because then, if this is the perpendicular line, then we can project to that third axis, I think. So, yeah, I'm somewhere. I think I'm onto something here. So this is negative 12, negative 14 I minus 4j plus k, which is the vector negative 14, negative 4, 1. So now our basis vectors are these three vectors, and it's like if we're getting somewhere. VW and the cross product of V and W. I got stumped. I always keep going until I get stumped. I think we're very close, though. If anybody in the chat has a hint for me, I would love to hear a hint. But, okay. So, this is these two vectors are perpendicular, or mutually orthogonal to V cross W. So, if we can like project big determinants. Yeah, what's up, Leo? Dude, no, big determinants are in this book. Page 1, this guy's just like n by n determinants. You can see it as the elements of the symmetric group. And I was just like, dude, this is not the book I was looking for. Like, page 2 or something, he's like, recall, that the number of elements in the symmetric group is n factorial. I was like, what the fuck? Okay, no, I wanted a linear algebra for engineers. This book is beautiful, though. The Shilov is just like hardcore, straight up, just determinants until you cry in like section 1. Was reading about circulants the other day, a certain type of determinant that led Frobenius to introduce the first characters of non-abelian groups. Ooh, that sounds cool. He could also tell that they would be very important. Yeah, don't tell Axler. Like, they do seem very important. They do seem incredibly... I remember some math professors being like, yeah, I was just working on calculating a determinant of some complicated object. I was like, that's cool. Determinant of calculated objects. Dude, Leo, I thought I was going to get through all these sections, through this section, which I got stumped on this one. But I think I'm on a good path. I haven't read the section. I'm about to give up and just read the section. Maybe you can give me a hint, and I would feel just slightly better, just slightly less stumped. But I think I'm onto something here. So the question is, find the area of the parallelogram in R3 determined by these two vectors. So I know that in R2, the area of a parallelogram is going to be the determinant of two by two vectors, right? But now we're in 3D space, so it's like I know that two linearly independent vectors in R3 span a plane. So it's like I want to find the determinant of those two vectors in that plane that they span. So if I project to that plane, then I can get some other 2x2 vectors that they project into or something. I don't know. Like, so my thought is, if I can find a linear transformation that maps from R3 to R2, then I would, the transformation of V and W would be two-dimensional vectors, and then the area would be the determinant of those two vectors. My thought is somehow I can use the third vector being perpendicular to V and W. Like the orthogonal third vector would be V cross W. And if I can take like 0 as the component of that, like then the other two vectors are lying on that plane. Does that make sense? Yeah, cross product is what I initially thought of. I think it's there. I think it's right there. Somehow, like I found the cross product and I have the two vectors, and so I don't know, the vectors look something like this or something. Who knows? Whatever. Like those three and V cross W. Then if this is the orthogonal third vector, then basically I just want to, like the plane that these two span, V and W, would be having a 0 component along this axis, right? Like, does that make sense, dude? Like, cross product is what I initially thought of. Yeah, me too. I'm so bad at drawing 3D, but like, you get what I mean? Like the plane that those two span, if we just stay in that plane, then somehow I can see these other two vectors as 2x2. Drawing 3D is so hard, dude. It's just hard. So, like, I feel like I'm onto something, but what is it? What am I looking for in that idea of, like, I want to project V and W to no direction in the cross product. I think I'm mixing two different ideas. I still want this transformation from R3 to R2. And I think that what I want is some kind of projection that will project a vector to that axis or so. Does that even make sense, what I just wrote? I don't know, man. Like, I want a projection to... I'm giving up. But I think I'm very close. I think I'm going to read the section and feel like I was like 80% there. You should teach kindergarten math. Yeah, I should just give up. I don't know what I'm doing. But I think there's a more direct way to get there. Okay. Yeah, I haven't read the section. This is an optional section in the book, so I don't think my class covered this when I took this years and years and years ago. But it feels like the sort of thing that, like, as a graduated bachelor's degree in math, I should be able to like construct this section on my own. But I tried. We didn't get there. We got close, I think. Let me read the section. Let's see. Definition 2, 4.2. An n box in Rm. Let A1 through An be n independent vectors in Rm for n less than or equal to m. The n box in Rm determined by these vectors is a set of all vectors x satisfying x equals t1a1 plus t2a2 plus ... tnan. Okay. If the vectors a1 through an are dependent, the set described as a degenerate n box. Degenerate. Okay. That makes sense. Yeah, the boxes. So we've got a nice little figure here. A1, A2. Oops, whatever. This is a 2-box in Rm, and there's another sketch of a 3-box. And we're just going to focus on these parallel lines to be able to draw this damn thing. Parallel lines. Tip to tail additions. Something like this. Something like that. And then shade that in, and this is a 3-box in Rm. We are accustomed to speaking of the length of a line segment, of the area of a piece of the plane, and of the volume of a piece of space. To avoid introducing new terms when discussing a general n-box, we will use the 3-dimensional term volume when speaking of its size. Notice that we already use the 3-dimensional term box as the name for the object. Thus, by the volume of a 1-box, we simply mean its length. The volume of a 2-box is its area, and so on. The volume of the 1-box, determined by A1 in Rm, is its length, length A1, because the determinant of a 1x1 matrix is its sole entry. Exercise 36 shows that this length can be written as blah blah blah. Let us turn to a 2-box, blah blah blah. Volume change factor of a linear transformation. Volume of a box. The volume of the n box in Rm determined by independent vectors. Okay. I think it's this. Dude. Yeah, 2017, absolutely. I have taught math to like little kids like that, actually. I do like doing it a lot. I think I'm quite good at it. Bro, like, dude, let's take a short break, but this is it right here. This is the way that we'll solve this problem. Theorem 4.7, volume of this n box is the square root of the determinant of A transpose A, where A is an m by n matrix with AJ as its jth column vector. So, dude, this is it right here. I was trying to figure out, how do I get a determinant with these 3 like of this like non-square matrix where the... Yeah, I didn't know this either, dude. Isn't this super cool? Like, I've never seen this before. So, okay, let's finish this first. But dude, 2017, don't let me forget. I've got something cool there because I've shown some like little kindergartner kids some pure math. Like, this isn't quite pure math. Like, this here, I do think is like somewhat pure math, like kind of math for math's sake. And that's what I want to be sharing with you. Like, 2017 is in like 9th grade or something, and he found me in my gaming stream and has followed me around now. Dude, math for math's sake is a really cool thing. Like, I call it like math as a hobby, but it's the same thing. It's just math for fun. Like, literally, if you talk to a math major or like a mathematician, a math professor, and you ask them, why do you study what you study, and that are like, well, my research is important for cryptography, blah, 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 but like, that's not why I do it. Like, dude, I just do it because it's beautiful. I like it. It's fun. Like, that is exactly what my math professors would say. They'd be like, well, you write on the research grants that it's useful for cryptography, but like, dude, I study this because it's beautiful. Like, that's why I study math. Like, people can study math for fun. Math is fun for some people. Like, the fact that it's hard is what makes it so fun. And it's like infinitely hard. Like, if you get into the mindset of like, yo, I was stumped on that problem, I spent a week, and then I finally solved it, and I got so much dopamine from solving it there, and like, you start to enjoy that process of like banging your head against the table on a difficult problem, and then finally, eureka, you solve it, and that just being like really fun. That's what mathematicians get into. But like, you could do that. You don't have to be a mathematician to do that. You can do that for fun, for yourself. Like, dude, like, you're not in linear algebra, but if you're hanging out here, even if you're just absorbing like 10% of what I'm talking about, math can be fun, man. Like, math can just straight up be a hobby. It can be fun. So I didn't know, I've never seen this theorem, but this is it. This is it right here. So I was wondering, like, how the hell do I get a square matrix if I have two three-dimensional vectors? Hell yeah, this is super cool. So the vectors that let's copy these right now, right over here. We just worked a bunch of easier determinant problems, and now we're going to see some cooler things, I guess. This is neat. This is really cool to me. I didn't know this one. -1, -3, -2, and 0, 1, 4. So I just wrote these. I guess I kind of wrote them backwards, but I wrote these as columns. You'll see. And then the transpose of a matrix. This is the matrix A, and then the transpose is like you just rotate everything. Every row you write as a column instead, and every column you write as a row. So the first column I'm going to write as the row, -1, 3, -2, and then the second column, 0, 1, 4, right? And now we can multiply these and get a 3x3 matrix. This is so cool to me. I've never seen this. So when you multiply matrices, you do a dot product of a row and a column. So here, -1 times 1 plus 3 times 3 plus 4. Right? And then let's do, we're again doing that row and this column. -1 times 0, 3 times 1, and -2 times 4. Right? Now let's do this row and this column. So we got 0 times -1, 1 times 3, and 4 times negative 2. And then finally, we have that row, 0, 1, 4, and 0, 1, 4. I guess they're all, well, no, they're not always dot products with themselves, but sometimes. 0 times 0, 1 times 1, and 4 times 4. Look at that. We all learned something today. This is cool. This is really cool to me. So doing those additions, we got 13, 14. We got negative 5. I gotta go in a second here, actually. Dude, next time that I can catch you at in a math stream, 2017, if you put in an orthonormal basis from the span of the 2 columns, this fact comes out. Yeah, an orthonormal basis. I'm gonna think about that, but I think I was like along that train of thought, like, because I was finding an orthogonal third vector. Orthonormal means that it's length 1 as well. But I feel like I was like on the right track in all this somehow. Negative 5 and 17. Okay, so now the determinant of A transpose A is going to be the determinant of this matrix, 14, negative 5, 17. Did I get this wrong? 13, 14. I think I got that right. 14 times 17 minus 25. Yo, I'm going to ask ChatGPT on this one because I got to go in a second. 14 times 17 minus 25 is 213. Let's see if that's what the back of the book says. Like, yeah, so, I mean, the cross product is an orthogonal third vector. Is an orthogonal vector to the span of 2. And then getting it to length 1 does something. I don't know. I don't get it. 4.4. Oh, square root. I forgot the square root symbol. Damn it. We're so close. Okay. Determinant of this stuff. The area is the square root of this determinant. Square root of 213. Y'all, that's it for today. Thank you. Thank you for watching. I gotta go. Like and subscribe. It's been a pleasure today. I'll show you a really cool math fact that I taught a kindergartner the other day, 2017. If I see you again sometime. Peace. Thanks for watching. Hit the like and subscribe. Hey, Heidi stuck around so long. Dude, that's awesome. Good to see you, Heidi. Your streams are so relaxing. Thank you, man. Thank you. Hit the like and subscribe, share with a friend, all that good stuff. Let's build a really cool math community here. Thanks for watching. Bye.